My name is Jeff Breidenbach. I'm very pleased to introduce Danny Kamsia, who is going to be presenting on an automatic book scanner. This talk began with an idea of showing this device to a single person, and that person invited two more people, and you are all here through the incredible power of recursion. So with that, Danny, come take it away.
All right, thanks, Jeff. Let me take a moment and shut it down. I'm just going to tell you about this book scanner that I built. But first I want to just show you a few examples of some book scanning technologies that already exist for comparison. The easiest way to scan a book, of course, is to cut off the binding and then stick it through a sheet-fed machine. There are machines that'll just feed each sheet through and scan it, very high quality. But the problem is you destroy the book. So what we're talking about here are non-destructive book scanners. So there's a large class of book scanners that are not totally automatic, where a person turns each page. And a lot of the time there are glass plates that flatten the pages out, and then there are cameras that take a picture of both pages. So you have to kind of raise this glass plate, turn the page, lower the plate, and then snap a picture. So it's pretty fast, but involves a lot of manual labor. There's actually a large community of people at DIYbookscanner.org that build their own, and they post instructions for how to build your own. So they make them out of cardboard and wood and all kinds of things that are lying around. There are some commercial robotic book scanners. There's quite a few that use some sort of robot arm, the same way that a person would turn a page. And Kirtas is one of these examples. So they have an arm that kind of suctions a page and they move it over to the other side. There's another that uses a very different method. This company is called Triventus, and they make a machine that has this V-shaped thing that moves up and down, and it actually suctions two pages against it while capturing images with a linear sensor along the tip. So it's really cool, and these are state-of-the-art machines, and they've gotten a lot of praise for being gentle to books. The main issue is that they're really expensive. One of these Triventus machines can cost on the order of $100,000. So this is a machine that I built, and I'm going to show you a brief video so that you can see some closer-up views of it. And then I can go into some of the technical details. So the general idea is this book is moving back and forth on top of this prism-shaped machine. There are linear sensors, just like in a flatbed scanner, that the book moves across and it captures an image of each page. And then there's a vacuum, in this case just a regular house vacuum that's connected to those slots. It's sucking air and it sucks the single page through. And that page goes across to the other side. The question was, how do you ensure that you only get one page? And that's the next thing I'll talk about now. Once this is done. Yeah, and then the images show up on a computer. In a directory. So it's really simple, and it doesn't involve very many parts, so it's not very expensive to build. So yeah, the question was, how do you ensure that it only turns one page? So I'm going to try and provide a very simple diagram of what's going on when a page gets peeled off. In this case, we have a stack of pages that are sliding in from the right, and I'm looking at them edge on. And they're sliding along this curved surface, and along that curve, there are slots where I'm applying vacuum suction. So hopefully it's obvious that one page gets sucked against this. The other pages don't actually receive any suction, so they will tend to stay straight and go across, and then they get divided by this piece of metal on this side. Now, it's still possible for two pages to kind of be stuck together. And to help out with that, in this prototype, there's actually air that blows up from underneath, like onto the edges of the pages, and that helps to separate pages if they're stuck together. So next I want to talk about why the channel that the page goes through looks so strange, why it's shaped the way that it is, and try to explain the motivation for that. And I'll try to explain it by explaining a few examples that don't work. So for example, if you have this prism shape, and I'm looking at a top view here, where a page on one side has to get from that side over to the other side. The simplest thing to do is to cut a slot, like a diagonal slot in that prism, so that the page can slide into it and go across to the other side. The problem you run into is when the page is in the middle of that slot, it actually has to kind of twist. The binding of the book stays straight, but the page has to twist along that slot, and that's something that it just can't do. So it's very likely for the page to tear. So the way that the machine is really shaped is a little bit more like this, where there's a flat section in the middle of that diagonal slot. So the idea is the page is coming in, and while the page is in that intermediate section, it's actually free to swing across to the other side. And so it can go to the other side without actually getting twisted. So that works a lot better. There's another problem you run into. So in this example, the slot for the channel is just a straight diagonal along that front surface. And there's another problem you run into if you have that straight diagonal and you're applying vacuum pressure to try and pull the page through. So this is trying to illustrate that. Basically, this is a side view, and here's the page coming from the right to the left. And the darker gray area is the channel where the page is sliding into, and the really dark slot is where the vacuum is being applied. That's where the slots of the vacuum are. So in this case, the page is coming from the right, and the corner of it is getting sucked up against those slots and curving around that curve. So as the page continues, you run into a problem where the page is being curved along this diagonal, and that curve reaches the binding. And the page, basically the motion of the book is forcing the page to bend near the binding, and that's something that it can't do. Basically, in order for the page to continue to the left, it has to pull itself off of that vacuum area. And if that requires too much force, then the page will just tear. So this doesn't work very well. The picture at the top was actually an earlier cardboard prototype that looked a little bit more like this, and that was the problem that it had. So the way the machine is actually shaped is a bit more like this. There's a diagonal opening near the bottom, and then the opening opens up vertically in the top part. So as the book is going across, the page gets suctioned against that dark area and curves around that diagonal. But at some point, the page reaches the part where this opening opens up vertically. And so the page is no longer supported by the surface that's on the right. So it's actually free to swing across to the other side. So if you have a shape like this, then the page can basically slide its way off of that vacuum section without applying too much force to the binding. Okay, so the sensors, let's see, I've got one here. So these are the sensors. It's a contact imaging sensor, and it's straight out of a flatbed scanner or a sheet-fed scanner. It's the same thing that they use. So it has an array of light sensors and pulses colors so that you can capture each color. And it actually did come from a sheet-fed scanner. We took it apart. We took apart a lot of scanners, actually. And it turns out if you take out the circuitry and these scan bars and just plug them together, you can use it just like that. You can tell the computer to scan and it thinks the scanner is just a regular Canon scanner, and it captures images. So there's very little software required, and we didn't have to do any of the electronics. One note about using these sensors is that the sensor is kind of square, and when you stick it inside of, this is an end view of the machine with the book open on top. When you stick it inside, you can't actually stick it all the way up into that corner. And that can present a problem because you can't capture an image all the way into the groove of the book. So if the book has very narrow margins or has content that's all the way into the groove, then you might not be able to see that content. And for this prototype, one way we improved that situation was I just took these sensors to a belt sander. And it turns out you can grind away quite a bit of that circuit board before the thing stops working. And that was enough to get us within about 9 millimeters of the groove, which is okay for most books. For a real machine, if you want to do a lot of scanning, it's probably better to use a different sensor. There's a lot of other scanners that use a CCD sensor, where they have a lens and they project the image onto a linear sensor. And in that case, you could actually project the image all the way from the corner. It wouldn't have this kind of square restriction. And yes, somebody mentioned increasing the angle of the corner at the top would help. And that's something we looked into a bit. One problem you run into when you make that angle larger, like 90 degrees, is that the book doesn't actually want to sit completely flat. So the curve of the page may actually still hide some of the binding from you because it's not totally flattened out onto the surface. Also, librarians generally like to they consider it very bad to open the book too far, and so if you can keep the angle of opening as small as possible, that's better for the book. So this is the result you get. It's a very flat scan, as if you had put the page onto a flatbed scanner. And the quality is exactly the same. So by default, I'm running this at 300 dpi. But you could crank it up larger if you wanted. And it's also a lot better than using cameras for scanning, because cameras, even though they may have a certain number of megapixels, each pixel is actually red, green, or blue. And in these scanners, when you say 300 dpi, you're actually capturing all three colors for each pixel. So it works a lot better. It has much higher quality. And these sensors are only like $20 compared to a very expensive camera that you would need. Yeah? The question was, how's the linearity of motion? Like, do I have to do any correction for the motion not being very constant? And it seems pretty good. We've looked at the images and haven't noticed any disturbances. The motor is a stepper motor, and it has a very controlled motion. And the belt that we're using is a timing belt, the same as in a regular scanner. Earlier, we had experimented with ways of correcting for that using kind of a pattern that's on this saddle. So yeah, I'll say a little bit about this. We're calling the saddle, the thing that moves the book back and forth. It has clamps on it to kind of hold the book in place. And another purpose of the saddle is it has these white strips on it, which are used for calibrating the sensors. So it's in the home position. Those strips cover up the sensors. So when you first start scanning, they figure out what color is white, and they calibrate to that. The other important function of these clamps is to help support the weight of the book. So if you don't have them, you run into a problem where, say you have a very thick book and you're at the very beginning or end of the book, so all the pages are to one side. That weight can cause the book to kind of sag, and it causes the pages to sort of curve near the binding, and that can cause problems for page turning, or the book could just fall off to one side if it's very large. Yeah. The question was, does this mostly work for hardbound books, or does it work for softcover books as well? And it does work for softcover books. I guess the support for the support from the clamps kind of works a little bit better for hardcover books, but we haven't run into any problems using it on softcover books. So yeah, the clamps on the saddle look kind of like that, and they help support the weight of the book. Basically, when you first start scanning, you set the book down somewhere in the middle, and then you adjust these so that they're just touching the book. And then from then on, if the book is to one side or the other, it helps to support the weight. So the motor we're using, I said, is a stepper motor. It's an M drive, and we have this timing belt that goes around the top and then down through the machine. And this motor actually comes with a built-in microcontroller. So, and pretty much the entire code for it is on the right. Basically, you pre-program it with the code that tells it how fast to go and when to change direction. And from then on, when you power it up, it just goes back and forth and does its thing. The extra thing that it does is it has a serial connection, and at the beginning of each cycle, it outputs a new line. And we use that for timing the actual scan so that we know when the motor's arrived. So the software for this is really simple. The scan image program that shows there, that's from an open source scanning library called Sane. And so we haven't made any, we didn't need to write any software for that. And we call that with a flag that tells it to capture an image every time you hit enter. That's the bash prompt. And so then all you have to do is take the line breaks from the motor and pipe them over to scan image, and then the machine runs. So one command. So there's some extra software that Jeff, who introduced me, wrote. This is just an image viewer, so it shows you the images as they're being scanned, and it's open source at the URL at the top. And it has a lot of great features, like you can click on a page number and you can see a mosaic of all the page numbers that you've scanned. And that makes it really easy to tell whether something went wrong during scanning, like you missed a page or you duplicated a page. Basically, you can look down these columns and see like 361, 341, 321, 301. You can see all the way down that everything went fine and that no pages were missing. Another way that we avoid problems and detect duplicate pages or missing pages is with a sensor that's right inside the machine. As soon as a page comes in the slot to be turned, there's a break beam sensor. So we detect exactly when the page arrives. And basically, if a page arrives at the wrong time or doesn't show up, then we know that something's wrong and the motor stops. So this sensor is connected directly to the motor, and that's part of that microcontroller program. So that's about all the details. Just to give an idea of where things are, this is the first non-cardboard prototype. So there's still a lot to improve. The first prototype on the top left, that's cardboard just from a dumpster that was outside the office. So it cost nothing, and it had a little air pump from an inflatable mattress, and that was actually able to turn pages, and it was really exciting. So I experimented with the shape of the page turning mechanism a few times, but this is the first actually model that's actually built out of metal. So where it is right now, basically, it's very quick to set up for a book. It takes about 40 seconds to adjust those clamps and start the scanning. The cycle time of this going back and forth right now is 11 seconds for a page pair. So a 300-page book would take about half an hour. This is a lot slower than many of the alternatives, but since it's fully automatic, one operator should be able to run like 10 of them. You don't have to do more than just start it and stop it. The materials, there's only about $1,500 of materials. About half of that is just the scanner that we took apart, and there's the vacuum and then the metal. So it should hopefully be very cheap to build. And yeah. The question was, is it possible to get any sensor feedback from the motor as to whether the page is hung up or tearing? And yeah, there are models of this motor where it will know if it's stalled, if something is stuck. And I'm sure there are models where you could also detect how much force it's taking to move. So yeah, if you wanted to get a fancier motor, you could do that. Yeah? What prevents me from running it faster? Right now, that's actually the motor. If I try to run it faster for a large book, then the motor doesn't have enough power to move it. So an easy way to make it faster is just to get a better motor. There's also things you can do with the arrangement of the sensors and the shape of the thing. Basically, just make it so that it has a shorter distance to travel. The question was, do you need any adjustments for book size or paper thickness? There's a limit to the size of books that this can be scanned, and right now, I guess I was going to mention we've only scanned about 50 books. Basically, about 60% of the books that we've come across are able to be scanned. Like many of them are too big or too small. So basically, it has to fit inside of the saddle, and it also has to be able to reach those vacuum slots. If a book is really small, then it won't reach them at all. And so that's a number that could also be improved by changing some of the dimensions, basically doing a bit more experimentation with how the thing is shaped. And then for thin pages or thick pages, one major factor in that is what the power of the vacuum is. So it's best if you can adjust that, so for very thin pages, you don't want to pull too hard on them. But again, there's a limit on what you can do for that. So this works on most books we've come across, but it won't work on like dictionary thin pages or really stiff kind of cover page material. So we still have a lot of problems. Basically, about 45% of books have 1 or 2 skipped pages that we tried. And about 45% of them have some sort of fold or tear in the page. And that's really bad. This image is an example of one of the bad cases. And actually what happened here was the page already had a little bit of a tear in the corner, and that presents a problem. So when it went through the machine, it kind of exacerbated that and folded it. Of the books, yeah, not the pages. So it's only a couple errors in the book. So for most pages, it was fine. We'll leave those questions until afterwards. That's all right. So yeah, and also this was before we installed the sensor. So in this case where the page was folded, it's very likely that the sensor would have detected that the page didn't arrive at exactly the right time and stopped the machine before it caused any more damage. So yeah, there's a lot of improvements to make. I still haven't experimented much with different shapes. This is only the 3rd iteration, really. And there's adjustments you can make to the vacuum, like maybe adjusting where the vacuum is applied and what the slots look like. There's better materials, like aluminum leaves a little bit of aluminum oxide residue that you can kind of see on the edge of the book. And it would be better if it were stainless steel or something like that. And of course, better image sensors like a CCD sensor that would be able to capture it all the way into the corner. And then there are crazier ideas, like you could take a whole bunch of these and chain them up if you have a lot of books to scan. Basically, this diagonal opening can be chained pretty close together. So you could have just 2 people, one at each end, loading books one right after another, and you could perhaps scan books really quickly that way. So there's a lot of interesting ideas about what to do with it. So that's it. I just want to thank Jeff, the person who introduced me. He's been really crucial to this project. He wrote all the software. He helped out with the sensors. He installed the brake beam sensor and helped take apart scanners. And he's given me advice all along the way. And given me the moral support to keep working on it. And also want to thank my manager Stefan and previously Ram, who have been okay with me working on this, and they've supported me in any way that they could. And so yeah, that's about it. I can take questions.
Can you talk a little bit about error recovery and what happens when different sorts of things go wrong?
Okay, the question was, can you talk a little bit about error and what you do when something goes wrong? So right now with this prototype, basically if a page doesn't turn, then that sort of detects it and the machine just stops. And so you can notice that and come and figure out what happened and then reset it and start it again. Right now there's no way to detect if two pages go through, if they're really stuck together. Then that means that you miss capturing the images of the page that was in between. So that's a problem, but there are ways that you can detect that, and there are things that like sheet-fed scanners use to detect whether two pages have gone through, and you can do something similar. And yeah.
Do you think you could make it significantly cheaper? And it's already pretty cheap, but it sounds like it's a pretty expensive scanner to use, and it kind of doesn't feel like it's already so cheap compared to most of the alternatives. That's not a big priority.
The question was, do you think you can make it any cheaper? Because it sounded like the scanner part was already the most expensive part. Yeah, if you did your own electronics, for example, these sensors, the part that we're actually using, are only $20 each. So if you built the electronics yourself at a large scale, then it would probably be even cheaper than it is now. But the biggest cost will probably just be putting it together. And right now, I mean, all the pieces are basically flat pieces of metal, and so they're very easy to cut. Other questions? Yeah. Question was, where did I build it? And I built it on some workshops that were on campus. Question was, what happens if the book is really dirty? Does it leave a streak all the way down the page? If there's really something like smeared on the paper, then yeah, that could like get stuck to the sensor and leave a streak, and you'd probably have to have some process to notice that and clean it up. But we've joked that since the book is traveling over these vacuum slots, we're actually cleaning out dirt from the book as it goes, and that's a feature. Any others? Mm-hmm. The question was, it looks like this machine, if something goes wrong, could actually tear a page, and it looked like the other machines we looked at couldn't actually tear a page. So the other machines, they do tear pages. It's just very rare, and they're gentle enough that libraries are okay with using them. For this machine, we've actually talked to the conservationist from Berkeley, and he was really excited, basically, that the benefit of having digital versions of these for people to use was greater than the risk, the small risk of causing damage to some books. And libraries accept the risk that, like, when they check out books, they are going to come back in worse shape than they were before, but that it's worth it for people to use the book and to read the content. But yeah, hopefully this can be improved to the point that it is safe enough to use on fragile books. Yeah. The question was, why is the scanner so far away from the slot? The main reason it's there was just we wanted to have both scan bars together so that they capture at the same time. And the slot, this side, the exit slot actually extends all the way up to where the scanner is. So you could actually make them closer if you had them separate, like one on this side and one on the other side. And that might make a shorter distance to travel. Mm-hmm. Question was, is it two scanners or just one scanner with two bars? This is one scanner with two. It's from a sheet-fed machine, so the sheet would feed through, and it had a scan bar on the top and on the bottom. And so we one circuit board, and we just took two sensors. All right, any other questions?
Where does this project go from here?
The question was, where does this project go from here? And I don't know, but we'll talk a little bit more about that later.
maybe this is a good time to end the recorded portion of the talk. And let's give Danny a hand.